I would like to introduce you to this topic. This talk will be a little bit more conceptual because this is an early research phase, but I hope you will get a sense of what do you want to achieve. Also, astronomy is not a very large field, so there is a lot of potential for ML here, so it's not oversaturated. So we are starting with large language models here. They are very popular nowadays in many fields, but as far as we know, this is the only real big application. But let's move to the topic. Oh, I'm so sorry, but okay, it works. So first of all, I would like to give a big thanks to our team. Our team is quite large. It's the UniverseTBD collaboration, and it's quite international. And also, again, a big thanks because everyone does it, I would say, in their spare time. So I am very proud of what we were able to achieve in 6 months, taking into account that everyone has research positions somewhere. And another acknowledgement is that I would like to thank our sponsor, G-Research, for funding my travel this year, and that our work has been supported by a grant from Microsoft. So let's move to the scientific part. And our question we would like to answer is how far can large language models go in terms of advisory for scientists? So are they able to gather the state of current knowledge and come up with a suggestion or a link between various findings? So we are not talking about summarization or question answering, but something more. And this is what's at stake here. So, of course, large language models need no introduction. Everyone has heard at least something about them. But there are some promising qualities of them. So they do demonstrate some emergent abilities, which we find very promising for our case. So that would be this question whether the large language models can reason, because it's even a philosophical one, so maybe not, but we would like to experiment with that. If they could, then we would have an assistant capable of suggesting what could we look into. And I will try to explain you why do we want to do that. So let's move to challenges in modern astronomy, which might be similar to challenges in many physical sciences, natural sciences. So, of course, the overabundance of papers, and astronomy is not a really big field, so it is even worse in medicine for sure, but it's still too much. So NASA ADS is a system that gathers referred papers in astronomy and physics, and just looking at the subfield of astronomy, we have over 1.3 million of papers, and as you can see, not surprisingly, the papers released are rising each year. So this is very hard. It's hard to keep up. It's hard to keep up for young researchers, and it's hard to get overview of different fields. So usually, this won't be surprising because everyone here is kind of in research, but you do focus on one subfield. And you can lose track of what's happening somewhere else just because you are human, and it's difficult to keep up. But also, the metrics that are used to measure the papers might be not the most efficient ones. So citations are a bit biased because if you have a lot of papers, the kind of classical papers, the examples that are well approved of, get more and more citations and might overwhelm the newer findings. So there is a paper that suggests that the canonical progress might be slowed down actually with the rise of papers. And another thing is measuring the similarity of papers. So it's super useful to have a recommendation tool, but it's a bit hard to measure it because keywords is not enough, and authors is also not enough. So embeddings are a perfect tool here. And now another challenge, this is not something that we are dealing with right now, but of course it's super important to machine learning in astronomy in general, is that the volumes of data are unprecedented, and that is not the case in all fields, but the data sets in astronomy are open source, and we don't have privacy concerns. They are mostly open source, not all of them, but most of them are. Just to give you a glimpse of what we are dealing with, the largest data sets are the radio data sets that deal with interferometry due to the nature of these observations, but can gather petabytes. So SDSS and SKA are future releases, but this is something we already need to think about. This is like a time span of several years. And now the idea is of supercharging astronomers' research with large language models is as following. So first, we'd like to think if we can see if the model can connect the dots. So as I have mentioned, it's easy to lose track of the subfields, and this is quite a promising idea to have an assistant who does keep track, because the underlying physical processes of various phenomena in astronomy are actually the same. So the laws of physics are the same. So we can observe various phenomena. For example, we can observe something, so radio astronomers observe something, then people who look at the general model of the galaxy, they see something else, the motion of the stars, and for example, this can be linked to the same phenomena, and both of these observations can be used to, for example, constrain the star formation model. So these are the challenges here, that one should be able to have a general understanding of what is happening, and of course it's extremely hard with this amount of papers and research done. And also no one is omnipresent everywhere to see what's happening. We would like to see if we can use the emergent capabilities of LLMs to just gather this knowledge and possibly suggest something new. And another idea of ours is to move the field a bit forward in the realm of democratization of science. So it's great that the data sets in astronomy are open, but still scientific papers are not that accessible. If you are starting a PhD and you are in a smaller institute, it might be a bit challenging to get an overview if you don't have many researchers on site to talk to, especially from different subfields. So this is something that we would like to progress in as well, to develop kind of an assistant here. And let's move to our results. So our latest product is LLaMA. So of course it's fine-tuned Llama 2, as you can tell from the name. It has been released. I'm one of the co-authors. I'm not the first one, so I have to give back here to our colleague Josh Nguyen. And this is a very new paper. And long story short, we have evaluated this model in two tasks. The first one was a text generation. We have trained this model on over 300,000 of arXiv abstracts. And for now, it was only abstracts. So abstracts are not everything. So it should be better soon, because we are moving towards training on full data. Full papers. And now let's see an example of a completion with GPT-4. And if you look at it, don't worry about reading it all, because I will tell you what's happening here. We have provided a snippet of an actual abstract. So it's about the Magellanic Stream, which is a substructure in the Milky Way, so just a stream of stars. And we asked the model to complete it, and you know, as you might expect, it's perfectly okay in terms of grammar. It doesn't really hallucinate, but it just tells us nothing. It's too general, which is not surprising again, because these models are meant to be general. So this is our evaluation, that the model is too general. It just The whole text is kind of obvious, one could say. So it's about let's observe the stars with photometry and spectroscopy, so the usual type of observations, and then let's use data mining and machine learning. So this is basically what GPT-4 suggested. And LLaMA 2 has hallucinated a little bit, so it made up some numbers, which are, they are not absurd, but they just tell us nothing, they are made up. So that's pretty to be expected. And now let's move to our results. So here we were quite pleased with the results because the model seems to have aggregated the usual catalogs and the usual methods that are more in depth than just the general methods used in astronomy over the last 20 or 30 years or even more. I'm not sure if I have the laser pointer. Oh, I actually do. So here it suggests a new method to select new candidates of the stream. And this method actually does make sense in principle because it mentions the Gaia EDE free catalog, which is a recently released catalog that is often used to detect substructures because it has a very precise velocity and positional data. So this is actually the thing. This is what you would think of first when thinking about studying substructures in the Milky Way. And it's true. So no hallucinations here. And then it mentions the Gaia isosurvey to follow up looking at the spectroscopy, which is again quite often performed to constrain the results. So first we look at the very general survey, then we tend to look at the spectroscopy because it's more precise and tells us more. Well, not more precise, it just have more information, but it's harder to do spectroscopy because you need a very long exposure time, so our resources are limited. So it does mention actual things, actual catalogs, and quite correct methods. So this is what we are hoping for. And the second task, maybe not task, but the evaluation metric is the embedding space. And this is, if this model performs well here, we could use it to build a reliable recommendation tool for papers, because the embeddings of the papers should be similar and they shouldn't be too narrow, because the GPT-3 embeddings are very narrow because all of these papers are about astronomy. So obviously, if the model is general, it will group them as similar. And our model has a very large, compared to GPT-3, range of embeddings. So that's great. This is what we wanted to achieve. It looks that it's going in the right direction. And just an example here. So this is the cosine similarity. So the first example here is two papers. They are on something actually very different. It's just both of them mentioned magnetism. And GPT-3 assigns a quite high scores because it gets fixated on the magnetism keyword. And LLaMA gives it a quite low score because it is actually not very related. Meanwhile, the second paper, it doesn't have any similar keywords, but it's actually about mid-infrared observations. So Spitzer is a mid-infrared survey. And the model seems to know that because here we have a Spitzer sensors, and here we have something about the mid-infrared halo, so observations in mid-infrared. And it assigns a quite high score. So that's good. And we would like to progress on this and build a recommendation tool that would take in a PDF of a paper and link to other similar papers, similar in terms of this embedding space score. So what is next? We are currently in progress on training a big LLaMA on the whole papers, not just the abstracts. And that might help with knowledge gaps in selected field. Because, of course, the abstracts are not everything. They don't have any fundamental explanations. They just have the general results, the general methods used, which is, of course, this is probably the most important thing to gather knowledge about. But fundamental knowledge is hoped to deliver this insight, but can really, really supercharge this model. Because the recent findings, recent experiments on the phi model shows that it's promising to attempt to train on a textbook quality data, and the model might actually get this insight of this basic logic. Well, logics or reasoning is maybe a too strong word, because we are still very unsure of what's happening, but still we could have a useful assistant. And the training data will be more diverse, because we can have Q&A paths, because our model doesn't do Q&A, so the democratization thing is a bit harder here if we don't have a Q&A. And astronomy has a lot of well-known textbooks that we can just use. We don't have to actually generate them. And some papers like annual reviews, which are much a better overview than just singular papers. We hope to patch up the gaps in knowledge of the models. So thank you so much for your attention. Here is the link to arXiv.